Elia Fioravanti from Karlsruhe Institute of Technology is going to tell us about automorphisms of GCs.
Great. So thanks a lot for the introduction and inviting me. So I want to talk about automorphisms of groups, and particularly what can be said about general families of groups and the automorphisms and the shared properties. So the typical question that I want to discuss is, let's say we start with some family of groups, F, say a family of finitely generated groups, or finitely presented maybe. And well, the typical question is then, what can we say about automorphisms? For instance, what can we say about the outer automorphism groups of all the groups in this family? The typical thing that I'm looking for, right, is how good are these groups? How good are these automorphisms? Somehow, is there a structure? Are they all sort of tame? Or can they be wild in some sense? So we'll make this precise in a moment, but this is a typical question. So there are plenty of reasons to study automorphisms. I mean, some are purely algebraic. It's a very natural construction, passing from a group to its automorphism group. You want to know how this construction behaves. And you want to know how properties of the group affect properties of the automorphisms. This is a transfer that doesn't always work. It's sometimes hard, also when it does. Then there are perhaps more sort of computational reasons. If you're interested in solving the isomorphism problem in a family, Dane's isomorphism problem, then typically the first step is to understand the automorphism groups of the groups in your family, and typically the techniques you use are similar. So these are related problems. And also, there are topological interpretations of outer automorphisms, right? So if your group arises as fundamental groups of some spaces, and if your spaces are aspherical, then outer automorphisms are exactly the same as homotopy equivalencies in the topological world. So there are many reasons why you want to look at this. And I just want to start by making some observation that here the family F is important. So you do need to restrict the families you look at quite a bit, because, for instance, there is nothing to be said about all finitely generated groups. So nothing to say about the family F of all finitely generated groups. And there are some results of Boumediene and Wise that I want to mention in this direction. Which are proved using small cancellation theory. Well, for instance, you can say exactly which groups arise as outer automorphism groups of finitely generated groups, and it's all countable groups. So group O is countable if and only if there exists a finitely generated group G that has out G isomorphic to O. So one arrow is very easy. The other one you can prove with a Rips construction. So you can get all sorts of things. A more natural question would be perhaps what can we say about outer automorphism groups of finitely presented groups? And there we don't know. We don't have a sharp answer. So Boumediene and Wise, also with Rips construction, they prove that all finitely presented groups can arise as outer automorphism groups of finitely presented groups. So this already tells us that this family is huge, but at the same time there are only countably many finitely presented groups, so there are only countably many outer automorphism groups, and there is maybe something to say. We'll see examples of finitely presented groups where the outer automorphism group is not even finitely generated, so this is really not sharp. It's not clear what kind of answer one might be looking for, but I wanted to advertise that this is a problem I find interesting. Okay. But as I said, so the point of this talk is about finding structure in automorphisms, so I should tell you what I mean by structure in this setting, and I want to do this by looking at some examples. And there are, in some sense, three automorphism groups that are unlike all others, that are particularly good, they're exceptional in many ways. And they should serve as the example for what it means to have good structure. And so let's say the three sort of classical structured automorphism groups are, well, the following three. Well, outer automorphism groups of free abelian groups. So here, it's not hard to see that we find GL and Z, right? Second example are surface groups, particularly closed surface groups, right? And if we look at a fundamental of a closed surface, let's say fundamental group of a closed surface, let's say even orientable, here the outer automorphism group is identified with the mapping class group, extended mapping class group, where we need to allow orientation reversing homeomorphisms. And a third example that doesn't require further explanation are free groups and the automorphism. And so free abelian groups, free groups, surface groups are very symmetric groups, so they have lots of automorphisms. In some sense, within any reasonable family, these three groups will be the ones that have the most automorphisms, and the automorphism groups will really behave in an exceptional fashion. So these are three infinite groups. They're complicated. They have a lot of structure that we understand, but at the same time, they're also quite tame. They're not exotic groups in a sense. And there are two particularly good ways that I want to emphasize in which these three automorphism groups are tame. And this is what I want to discuss now. So there are, let's say, at least two ways in which these groups have tame automorphisms. Okay, so the first way has to do with the global structure of the outer automorphism group. So in particular, if you look at GL and Z, mapping class groups and out of N, these are all finitely generated groups. So these are extremely old classical results, so they were proven in the 20s even. So it's Dane for mapping class groups, Nielsen for out of N, I think. And they were shown in the 1920s. For GL and Z, I'm not sure this is to be attributed to anyone. It's not so hard to see that elementary matrices work. Magnus proved finite presentation a bit later. And nowadays we know they're not just finitely generated, they're finitely presented. There are even of finite type, up to finite index. They are virtually, let's say, of finite type. So they have torsion, but if you pass to a finite index subgroup that doesn't have torsion, then they're fundamental groups of aspherical cell complexes with finitely many cells. So in this sense, they are really non-exotic groups from this perspective. So here, I'm not entirely sure who to attribute this fact to, because there are various ways of seeing it, but I would say it was proven between the 60s and the 80s, and one way of seeing this is by finding good compactifications of spaces, or moduli space, or locally symmetric spaces. So for GL and Z, it follows from work of Borel and Serre. I'm not sure if it's even older in this case. Here, it follows from work of Deline and Mumford with some work, and here I would say Kaller and Botnick. Okay, so in this sense, these are well behaved, but I want to emphasize this is not what always happens for outer automorphisms. And so there's a classical example, so they would call Wild. This has also been known for a long time, at least since the 80s, and it's certain bound slug Soiter groups. So for instance, 2, 4, so here's a presentation, two generators A and B conjugates the square of A to the fourth R of A. Here the only thing that matters is that none of the two integers is 1, and that 1 divides the other. That's what the important part. And here, well, out G, this is a finitely presented group for sure, but out G is not even finitely generated. This was shown in the 80s by Collins and Levin. And then many people studied automorphism groups of Banzer's solitary groups afterwards. Particularly Levitt and Clay proved various properties of these automorphism groups. So if you're wondering, how it fails finite generation, here this group is actually locally virtually free. So every finitely generated subgroup is virtually free, but you do have torsion of unbounded order. So it's not too bad of a group, but it's sort of wild. Okay, so this is one aspect. And the second sort of way in which those three groups have tame automorphisms, this is the second way I want to mention, has to do with growth rates. So not the structure of the entire automorphism group, but just the behavior of single automorphisms and sort of the dynamical behavior as they act on the group. So here the fact is, so for these three groups, G, free abelian, surface group, or a free group, each outer automorphism has only finitely many growth rates. So I'll define growth rates in a moment, but the rough idea is I fix an element of G, I apply higher and higher powers of my automorphism to my element, and I see how fast the complexity of this element grows, measured in terms of conjugacy length. And as you vary the element, there are only finitely many possible speeds of growth, and these speeds are all of a particularly simple form. So let's say polynomial, or polynomial times an exponential. And the exponentials always have base lambda that is an algebraic integer. In fact, not any algebraic integer, but a weak Perron number. So something such that if you look at all its Galois conjugates, have absolute value that is possibly equal, but not bigger than lambda. Okay, let me define growth rates, maybe a bit more precisely. And you can do this for all finitely generated groups in their automorphisms. So let's consider group G and a finite generating set S. And this, of course, gives us a word length, which I denote by single bars, a word length function on G. And I can talk about conjugacy length, which I denote by double bars. So this is just the infimum of word length over the conjugacy class of G. And this has a nice geometric interpretation, right? So if your group G is the fundamental group of a compact manifold, compact Riemannian manifold, even without any curvature assumptions, for each free homotopy class, you can look at the shortest length of a closed geodesic in this homotopy class, and up to constants that only depend on the manifold, this will be the same as this algebraically defined conjugacy length. So it's then natural, if you apply a homeomorphism to a manifold to see how fast the growth of the shortest length of a geodesic grows. And that's what we want to do. So right, the growth rate of an element G in G under an outer automorphism phi is a sequence, or rather the equivalence class of a sequence, so the sequence you want to look at is precisely the one that assigns, you look at the sequence of conjugacy lengths of the orbit, of the elements in the orbit of G under powers, positive powers of phi. So here I'm applying an outer automorphism to a group element, which is not great, but you can think of this as a conjugacy class rather than an element, since conjugacy length only depends on that. And the equivalence class is just by Lipschitz equivalence of sequences. And I need this so that whatever I define is independent of the choice of generating set that I made at the beginning. So were a sequence AN is equivalent to Bn if there exists a constant C such that AN over C is at most Bn, at most C AN. So it's by Lipschitz only, you only post-compose with a by Lipschitz equivalence, but not, N is, stays N. So this is a sharper equivalence relation to the one that Martin considered in the previous talk. And it's important because the coarse relation we saw in the previous talk only, it doesn't distinguish between exponentials, or exponentials are the same, but here I can remember the base of exponential growth. So lambda is part of the data that I'm remembering. Yeah, polynomials are determined by their exponent and so on. And yeah, if I change the finite rating set, conjugacy length changes by a global, by Lipschitz equivalent on the group, and growth rates are left unchanged. So growth rate only depends on G and phi. And now, so here, this it's a collection of various theorems. But what I'm saying is, a priori, you can apply phi to infinitely many conjugacy classes, and a priori you could find infinitely many different speeds of growth, but for these three groups you only see finitely many. How many is actually independent of the, or it's bounded above independently of the automorphism, it's bounded above purely in terms of the group, and the speeds of growth have this particular form. And should sort of say who proved these things. So for Z to the k, this is a standard exercise in linear algebra. So you can deduce it from the existence of Jordan decompositions. Lambda will always be the absolute value of an eigenvalue of the matrix. You can do the Jordan decomposition over C, that's fine. And Jordan blocks will give you these polynomial terms in front. For surface groups, this is a standard Nielsen-Thurston theory. So you have a Nielsen-Thurston decomposition from the Fourier homeomorphism. So you have some collection of curves, finite collection of simple closed curves that are pairwise disjoint on the surface that is left invariant. And then on the complementary regions, you are maybe finite order, or maybe a pseudo-Nosov, maybe you Dane twist around the curves. And in terms of this data, you can easily understand how fast the growth how fast the length of a curve grows. And surface groups are particular in that you never have this polynomial term in front of the exponentials, unless you are polynomial. But if you're polynomial, you either stay bounded or grow linearly. You never grow faster than linearly. So it's a bit more restricted. And for free groups, this is, well, the last case that was settled. It's, I would say, considerably harder than the other two. And it's particularly hard to control, if you start with a word and apply your automorphism, it's very hard to control cancellation. But you can't do it just combinatorially or hands-on. You really need some techniques inspired by topology, sort of inspired by Nielsen-Thurston theory. So these were developed by Besvine and Handel, and also improved then together with Fein in the 90s, so yeah. And the person who actually wrote down a complete proof of this result is Levitt. Okay, and just to conclude this discussion, I owe you a wild example. And these are sort of harder to come by. So I don't have any natural groups where this fails. But Rémi Coulon recently constructed, again using small cancellation, some examples. So there exist finitely generated groups, which are unfortunately not finitely presented, that admit some automorphisms of intermediate growth. So with phi, an outer automorphism, growing up to a coarser equivalence relation that I'm not going to discuss, faster than any polynomial, but slower than any exponential. So for instance, an exponential where you have a square root in the exponent. So these are the only examples we have, but this is an interesting problem, understanding what growth rates can arise. And the point is we just know very, very little. So we understand essentially those three classical groups and a few families that we'll discuss that you can reduce to those three classical groups. But for most groups, we don't know what can arise as growth rates. Already in those groups, it can be very hard to control growth, but it also seems to be fairly hard to come up with exotic examples. And there are all sorts of questions that you can ask here that we don't know the answer to. So do we have finitely presented groups with intermediately growing automorphisms? We don't know. And even among finitely generated groups, I think it's unknown whether an automorphism can have infinitely many growth rates. Presumably yes, but we don't know. You can wonder, what bases of exponential growth can arise for finitely presented groups. It's clearly only countably many, because you have countably many finitely presented groups, and each of these groups has only countably many automorphisms. But it's not at all clear that this countable class of real numbers should be algebraic integers. Presumably it's not. Okay, so this is the situation. Are there any questions so far? Okay. But so far, all my discussion has been about concrete groups, specific explicit groups where you have a simple presentation, or an elementary presentation, an explicit presentation on a nice classifying space. You have many tools to study automorphisms, but I promised I will talk about families. And for families, it's sort of, it's a fairly different problem in a way, because you are always working with a mystery group. You don't know your group. You only understand a certain aspect or a certain property of the group, and you need to translate that into information about automorphisms. And so you can start to wonder. So you can look, for instance, at the universe of all finitely presented groups. And I'm thinking of Brightson's picture of this, which I won't draw. But the idea is, right, you start, your universe starts with the trivial group or finite groups, where you understand automorphisms because there basically aren't any. And then you move away into the universe, away from the trivial group. Groups get more and more complicated, and you can wonder, where does my understanding stop? So how far can I go from the trivial group and still understand automorphisms? And there are many directions you can do this along, but there are two that are, the most natural ones or our favorite ones. And these two are, well, amenable groups, so groups that are sort of small, abelian, nilpotent, polycyclic, solvable, and so on. And the other are groups with some sort of non-positive curvature properties. So hyperbolic groups, zero groups, maybe some form of commutability, and so on. And I can tell you, in these two directions where our understanding stops, quite precisely. And I think this is a fairly complete summary of what we know about general families of automorphisms. Okay, so I'm going to start with amenable groups. And here we understand things all the way up to polycyclic. So if F is a family of polycyclic groups, we know that their automorphisms are fairly tame. And here, I think the state of the art is more or less a result of Bauers and Grunewald, who showed that here out G is always arithmetic. So it's arithmetic over Q. So yeah, this is due to Bauers and Grunewald about 20 years ago. So the weaker results are much older. For instance, already in the 70s, Auslander proved finite presentation when G is nilpotent, finitely generated nilpotent. And here arithmetic implies finitely generated, it implies virtually of finite type. So here we have the best possible tameness when it comes to the global structure of the automorphism group. I think growth rates are unknown. I think they're unknown because people haven't looked at it. I don't think this is a structurally difficult problem, but I don't know what the structure of growth rate is. What I want to emphasize, however, is that if you try to push this, push past this into the world of solvable groups, for the time being, we don't know anything, I think. So about general structure. So we'll advertise this question. I think it's unknown whether out G is finitely generated for, let's say, G finitely presented solvable, for instance. You might want to put something more like, finite rank or Q linear, and perhaps there are some questions that, perhaps these are properties that help, but I don't think we have a general understanding here. Okay, and we can then talk about the world of non-positively curved groups.
For metabelian?
Sorry? For metabelian, I don't think it's known either. But, or at least I don't know any results about metabelian. And solvable groups, automorphisms of solvable groups behave sort of differently. So here, for virtually polycyclic, for instance, the isomorphism problem has been solved in the 90s by Dan Siegel. For solvable groups, it's already for step 3, I think it's known to be unsolvable by work of Karlsruhe in the 80s.
For metabelian, there may be a chance.
For metabelian, it's a good, I mean, it's not clear that the isomorphism problem is related to the structure about G, right? But for metabelian, it's perhaps still true. I do not know.
We'll give you negative examples for that with Neumann test.
Sorry?
Neumann test can give you negative examples.
Okay. Okay, so non-positive curvature. And here, the extent of what we know is essentially limited to hyperbolic groups. So we understand everything for hyperbolic groups, but not much beyond them. So if F is the class of word hyperbolic, maybe I go there actually, a bit more space. So if F is the class of word hyperbolic groups, and this will work also for certain relatively hyperbolic groups. But you know, here our understanding is due to the work of Rips and Seller, who you know, had some impressive, amazing breakthroughs in the 90s. And one of the first things that they proved with the theory was indeed that out G is always finitely generated. And the original argument is quite abstract, right? It's based on the shortening argument. But then soon later, Seller developed JSJ decompositions for hyperbolic groups, showed they're canonical. And once you have JSJ theory, it's really not hard to actually prove that it's virtual finite type. Because you can essentially describe this in terms of mapping class groups and related, other constructions, but constructions we understand. And when it comes to growth rates, again, the structure is good. It's the same as in our 3 favorite groups. So each outer automorphism has finitely many growth rates. In fact, boundedly many, only depending on the group. And again, all are of the form polynomial times exponential, and the base of the exponentials are algebraic integers. Here, they're actual Perron numbers. So the weakness in weak Perron numbers is due to Zn, usually, but free and surface groups don't have this kind of behavior. And here, actually, if your group is one-ended, then you don't have the polynomial term in front. And you get the same kind of growth behaviors of surface groups. Okay, this is due to Coulomb, Ilion, Orbet, and Levy. They have a preprint that is fairly complete, but it's not out yet. You use, of course, JSJ theory and Rips-Seller theory, but torsion creates issues, and also you have issues related to the fact that growth and graph of groups are related, but they don't behave super well with each other. Okay. But you can try to wonder what happens beyond this. And in particular for cat zero groups, we don't know anything, anything in general. And the point here is that our understanding of automorphisms of hyperbolic groups is due to the fact that Rips and Sella proved that, or Besvin and Fein, maybe, better reference. So they proved that a hyperbolic group G can have many automorphisms only if it has a very particular algebraic structure. So infinite automorphism group is only possible if your group splits as an amalgam or a Chern extension over a virtually cyclic subgroup. In which case you can actually see automorphisms quite concretely via an algebraic construction called a Dane twist. Or at least some of them you can see in this way. For cat-zero groups, we don't have such splitting results. And in particular, it's not hard to construct examples. Already some right-angled Artin groups do this. You can find RAGs that don't have any abelian splittings, but still have infinite outer automorphism group. So things are significantly different. And in general, we don't know. But in relation to this, I want to mention a question of Rips, who was maybe a little bit less ambitious, and asked, what can we say about out G for co-compactly cubulated groups. So groups acting properly and co-compactly on a cat-zero cube complex. And I don't know what his motivation was, but one way why I think this is interesting, one reason is that, so a key point in the theory of automorphisms of hyperbolic groups is that hyperbolic spaces degenerate into R trees. So if you have an infinite sequence of automorphisms, you can construct an infinite sequence of actions on hyperbolic spaces, and if you rescale them in the right way and take a limit, you find a non-trivial action on an R tree, because asymptotic cones of hyperbolic spaces are R trees. Here, cube complexes degenerate into 5-dimensional median spaces, so some higher dimensional version of an R tree that still retains a lot of the combinatorial flavor that R trees have in comparison to a general cat-zero space. So you can then wonder, here an important ingredient is the Rips machine, which allows you to understand actions on R trees and extract some simplicial trees out of them. And so here you can wonder, is there some higher dimensional analog of the Rips machine that will work? That is probably, this is something we don't know how to do yet. So it's probably a hard question. The point I want to make is that if you restrict the class of co-compacted cubulated groups just a bit, and look instead at the compact special groups of Haglund and Wise, then you can make do with what we already have. The standard Rips machine works, it's enough, and you can show that for these special groups, automorphisms are tame. There are other difficulties to overcome. R trees, you can construct them, but they're not as canonical. You always have to work with finitely many at the same time, which creates issues, but nevertheless, there is a theory that just using classical Rips theory understand automorphisms for special groups. So I should now give some definitions. Questions? Okay, so a group is special this class of groups was introduced by Haglund and Wise, who were interested in this for completely different reasons, but it's nevertheless a very interesting class of groups to study. So a group is special if the original definition would be if G is the fundamental group of a compact special cube complex, so some family of non-positively curved cube complexes. But I want to give sort of a simpler definition, which is equivalent. So if G embeds in a right-angled Artin group in a particular way, so it's a right-angled Artin group as a convex co-compact subgroup. So convex co-compactly. So, okay, what do I mean by this? Well, right-angled Artin groups have a natural classifying space, the Salvetti complex. So they are fundamental groups of these nice non-positively curved spaces. and you can look at the action of the RAG by deck transformations on the universal cover of the Salvetti complex, and you talk about convex co-compactness in there. So that convex co-compactness means a subgroup is convex co-compact if it leaves invariant a convex subcomplex of the universal cover of the Salvetti and acts co-compactly on it. And it's the same, it's equivalent, and it's, however, important to remember that the embedding here is very non-canonical. You can have embeddings with very different kinds. Nevertheless, you just want the existence of one. Okay, so some examples in order. So first item are the three groups I've been talking about. So free groups, surface groups, and free abelian groups are all special. So we'll have to worry about them. Second natural example, immediate from this definition, are right-angled Artin groups. And right-angled Artin groups have interesting automorphisms that we don't completely understand still. Of course, free groups and free abelian groups are again a special case here. So general automorphisms of RAGs are sort of, will have a mixture of behaviors of automorphisms of free groups and automorphisms of free abelian groups. Other examples are many Coxeter groups. So, for instance, all right-angled Coxeter groups up to finite index. Because, well, Coxeter groups have torsion, and you need to be able to get rid of that. And in fact, I think conjecturally, I think all Coxeter groups are expected to be virtually special, but we don't know this yet. This is open. We know, so Haglund and Wise showed that all Coxeter groups virtually embed in a RAG, but we don't know if you can always find a convex co-compact embedding. But I think conjecturally, yes.
Whose conjecture is that?
I think they write it in the paper. I think they state it at the end. I can't remember if it's a question or a conjecture.
Because many people conjecture the opposite.
Okay. Well, I mean, I think it's a reasonable question because flats in Coxeter groups, affine flats really don't interact with each other, where they have finite projection onto each other. All obstructions that I know to being co-compact accumulated are based on interactions between flats. So if all interesting flats have finite projection onto each other, I think it's a good question. Anyway, another example, maybe let's put in graph braid groups. Fundamental groups of configuration spaces of particles on a finite graph. And I will conclude with the most interesting example, which, however, is not particularly interesting for us today. So fundamental groups of finite volume hyperbolic free manifolds. Again, only up to finite index. And I'll put this between brackets because, well, these guys by Mostro rigidity have finite outer automorphism group, so everything I mentioned here is sort of trivial. But also they're hyperbolic or relatively hyperbolic, where you have much better theory to study automorphisms. But I want to mention them because they're sort of an unexpected example. And they're a surprising example, and this really shows how broad the class of special groups can be. Okay, so it's time for theorems. So, how do you... Am I meant to use these to erase, or? Oh, yes. But maybe let's try with this. Right, and essentially I want to discuss two theorems about automorphisms of special groups, and they have to do with those two ways of being tame, which to some extent, up to a point, are satisfied. So, theorem 1, and this is not on the archive yet, but it should be soon, before the end of the year, hopefully. And if G is any special group, then the outer automorphism group is finitely generated. You can, of course, wonder about finite presentation, virtual finite type, and I think it can be handled by these techniques. I think finitely presented is as hard as virtual finite type here, but it is harder than finite generation, and there are good reasons for that. So I do not know how to improve this for now. So for people who are big fans of hyperbolic groups, I will mention that actually, so you can do this. It's finitely generated in a particular way, right? It's virtually generated by Dane twists. So in fact, out G is virtually generated by finitely many Dane twists. And here, so Dane twists are this sort of algebraic construction that imitates Dane twists on surfaces, something you can perform whenever your group splits as an amalgamated product or each in an extension, if the edge group has non-trivial centralizer in one of the vertex groups. You can construct these Dane twists. And well, in the hyperbolic world, Dane twists with respect to splittings over virtually cyclic groups virtually generate. Maybe you need torsion-free, not sure. But here, I've mentioned already for rags, you might not have any abelian splittings even, despite out G being infinite. So you need to look at more general splittings, and so with respect to splittings over centralizers. So centralizers here are meant as centralizers of subgroups of G. You take a subgroup of G, without loss of generality finitely generated, and you look at its centralizer. And these centralizers are a very rigid, very well-behaved class of subgroups, not abelian in general, but well-behaved. You need to add something else, because as stated like this fails for Z to the N, because in Z to the N, the only centralizer is everything, and you don't split over everything. So over centralizers or coabelian subgroups of centralizers. So something that is a normal subgroup of our centralizers, and the quotient is abelian. So yeah, in hyperbolic groups, centralizers are virtually cyclic, so this is looking plausible, right? But in general, that's the thing. About the examples there, this was known for rags. It's been known since the 90s. Lawrence and Sabatius constructed an explicit generating set for out of a rag. And up to passing to finite index, you can check these are indeed Dane twists, up to discarding some finite order elements. I think already if you pass to a finite index subgroup of a rag, I think this was unknown. And again, it was known for the entire automorphism of an entire right-angled Coxeter group, but if you pass to finite index, I think this was unknown. Okay. Theorem 2, this is already in the archive, and has to do with growth rates. And here, you can do this for virtually special. It's not. So for the moment, it's not. And you can phrase it, proving it for virtually special is the same as proving for G special that centralizers of finite subgroups are finitely generated. That is trickier. It's trickier. And that is a situation in which the fact that the R trees you construct, the fact that they are not canonical, they're sort of good R trees, but then they don't have a claim to being the best R tree, creates trouble. I think it can be maybe done, but harder. Okay. So if G is virtually special, here, virtually, it's not saying much. You can always pass to a characteristic finite index subgroup and get away with it. There are other structural properties you can prove for all virtually special groups. So if for any virtually special group, you can show that out G has finite homological dimension, or that it satisfies with its alternative. That you can do for virtually special, but finite generation is, yeah, tricky. Okay, so growth rates. And again, in full generality, I do not know if there are only finitely many growth rates. I do know this for some automorphisms, I'll get to that in a moment. But you can, for instance, prove that the stretch factor is an algebraic integer. So you look at the fastest base of, the biggest base of exponential growth, and this is an algebraic integer, always. So for all outer automorphisms, the stretch factor, which we can define algebraically like this. So for any element of G, we can look at the usual sequence, and we measure its base of exponential growth, which we do by raising to the 1 over n and taking an instop. So this sort of spits out the lambda, and we take a supremum over elements of G. So this is always finite, for all finitely generated groups. This is always finite, and here it's an algebraic integer, and actually it's again a weak Perron number. Okay, secondly, you don't have these intermediate growth behaviors. So the stretch factor is also always at least 1. And it's exactly 1 precisely when the automorphism grows sub-exponentially. And if it grows sub-exponentially, then it grows at most polynomially. If it grows exponentially, so if the stretch factor is bigger than 1, actually, you can show that the stretch factor is realized on a subgroup that is basically a free group, or a free abelian group, or a surface group. So if the stretch factor is bigger than 1, if you have an interesting automorphism that grows exponentially, then you can find an invariant subgroup that is nice, sort of again special, quasi-convex. And on this subgroup, you realize the stretch factor, and this subgroup will be a surface group, not quite a free group, maybe a free product, and not quite a free abelian group, maybe just something that has a free abelian direct factor. At least z squared is a direct factor. Okay, so this is also why sort of stretch factors, in a way, they're still the same numbers that you find in the 3 classical examples. Yeah, finally, for certain automorphisms, actually an important class of automorphisms, there are indeed finitely many growth rates. So if phi is what's called coarse median preserving, but this is actually, I can give a very intuitive explanation of what this means, but I'll do it in a moment. So if phi is coarse median preserving, then phi has only finitely many growth rates. And each of these growth rates, and each is either sub-polynomial, and the sub-polynomial ones are extremely hard to control, so I do not know if they're exactly polynomial. So either sub-polynomial or exactly of the form polynomial times exponential with lambda, again, weak Perron number. Okay, so what is coarse median preserving? Very roughly, it means it should not perform any skewing. It should not have the behaviors that automorphisms or free abelian groups sometimes have. It should not. Yes?
So the sub-polynomial being weird doesn't affect the last. So
it does not. It does not. And the key point here is that the sum grows faster, but this sum grows at the same speed. So if you have an exponential term, that saves you. There are, yeah, this is only a part of the problem, but this is the key difference. Yes?
So in one, can you replace the software with the other?
Yes, yes, because actually for the top growth rates, if you call lambda the stretch factor, you can show that the top growth rate lies between lambda to the n and bounded polynomial times, a polynomial with bounded power and lambda to the n. So since you can sandwich it like this, then when you do that, it does converge, yes.
So does that mean that you have the stretch factor for every single G is algebraic?
No, the stretch factor is always the top one. In the coarse median preserving case, yes. In the general case, for an element that is not fastest growing, I do not know.
But is there a conceptual reason why it might not work, or is it just technical?
The conceptual reason is that here, so the way you understand coarse median preserving, the point is accessing these lower growth rates. In the coarse median preserving case, you can construct some kind of Nielsen-Thurston decomposition, where you sort of hierarchically start decomposing your group. You have fastest growing elements, and then you look at the locus of all elements that grow slower. And here you can show that it's finitely many conjugacy classes of subgroups that are the locus, and these subgroups are invariant or permuted by phi, and they're again special, they're quasi-convex. And you can perform some inductive procedure, you need to show determinants in finitely many steps, but eventually every growth rate is the top growth rate on some invariant subgroup that is still special. Here, in the general case, if you perform this construction, after the first step, you can construct examples where you're infinitely generated. And understanding automorphisms of infinitely generated subgroups of RAGs is not something you can do in all likelihood. So it's infinitely generated subgroups of a particular kind, of course, but it is a trickier problem. Okay, so not doing so well on time, but just a word. So coarse median preserving just means you don't skew. So you don't have subgroups. If you don't have subgroups that are a product of this form, where this factor is getting skewed along the center. Because the RAM decompositions of subgroups are not canonical if you have center. And you want to avoid this trouble. Automorphisms of hyperbolic groups satisfy this. All automorphisms of right-angled Coxeter groups also satisfy this, sort of just happens. And for RAGs, these automorphisms are called untwisted. It's also a very interesting class of group of automorphisms that has been studied. And all of these results, I think, were open for RAGs. What I want to emphasize is that, I don't claim that there isn't another proof of this result, but the proof I give, even if you only care about RAGs, you really have to prove the entire theorem for all special groups. Because in this hierarchical decomposition, after the first step, you need to understand automorphisms of subgroups that are not RAGs anymore. And you can really construct examples where this happens. Okay, we'll take 1 more minute to just say 2 ingredients. Don't want to say anything about proofs, but I want to mention 2 things that go into them. And namely, Ritz theory, R-trees, and some kind of JSJ decompositions. So, proof ingredients for G special. So ingredient number 1 is that if you have an infinite sequence of outer automorphisms, if you apply the Spina-Polan construction to the right spaces, you find some R-trees, non-trivial R-trees. So these R-trees won't be small in general, and this is good, because we know that there aren't abelian splittings in general, even if you have many automorphisms, but they will be stable. And arc stabilizers are good. So whose arc stabilizers are, again, centralizers, or coabelian in a centralizer. And again, these R-trees are not quite canonical, but these are good properties, and you always have to work with far too many of them, which makes things like shortening arguments very hard to prove theorem 1, because as you shorten one of the trees, you will lengthen another one a priori, and if you only look at one tree, you're only seeing a portion of the automorphism, you're not seeing it all. So these are issues. And another thing that is more helpful for growth rates are JSJ decompositions. So, so if G is one-ended, JSJ theory you can only perform for one-ended things. This kind of stuff, applying the rich machine, you can extract simplicial splitting, so amalgamated product or H&N splittings over centralizers, and then you need to sort of understand all of these splittings in some way. And I will just say very vaguely, for one-ended groups, G has a canonical JSJ decomposition, so an out G invariant. JSJ decomposition, so really a graph of groups splitting that is preserved by all automorphisms, possibly trivial, JSJ decomposition over centralizers, so all edge groups are centralizers. And in order for it to be canonical, you need to do it relative to products. So all subgroups that split as a product of two infinite things should be elliptic. So you have this JSJ. For some groups, this JSJ is going to be trivial. And this is possible even if you have many automorphisms. But if the JSJ is trivial, you can understand automorphisms by its restriction to far too many subgroups and obtain an understanding that is sort of hierarchical. I will stop now. Sorry for going so, over time.
Are there any questions?
Say again, what are the spaces you take cleaving to get R2?
Yes, I did not say it. So RAGs act on some natural products of R trees. Essentially, you have the H&N splittings that you get by removing one vertex from the defining graph. Or you look at the Salvetti complex, you look at one orbit of hyperplane, and then you look at the dual tree. So RAGs act on this product of R trees. The Salvetti complex embeds isometrically equivariantly in this product of R trees, and you work with these. And they're very not canonical because they depend on the RAG. And also, the simplicial trees, the arc stabilizers, are meaningless subgroups for G. They're not, they're not centralizers, they mean nothing from an algebraic perspective. They're not preserved by automorphisms, but if you look at very, very long arcs, you can always perturb them into an arc whose stabilizer is a centralizer. And this is sort of the key to constructing this.
If there are no more questions, let's thank you again.